So in this lesson, we're going to cover a very common type of sequence called an arithmetic sequence. We're going to look at the recursive and explicit form of an arithmetic sequence. And we're going to find the sum of a sequence, which is called a series, using summation notation. A sequence is arithmetic if there's a common difference between each term. In other words, an arithmetic sequence goes from one term to the next by always adding or subtracting the same value. You can identify the common difference, d, by finding the distance between any two terms starting with the second term or higher. And the book writes it this way: u sub n minus u sub n minus 1 is equal to d for all n greater than or equal to 2. So here's a sequence, and we first want to identify if it is in fact an arithmetic sequence, and if it is, we'll write down the common difference, and then we'll define this in a recursive form. So remember, an arithmetic sequence is one where every term is a fixed amount more than the preceding term. So we can see that from -5 to -2, we are increasing by 3. From -2 to 1, we're going up by 3. And 1 to 4, we are going up by 3. And 4 to 7, we are going up by 3. So this is in fact a arithmetic sequence where the common difference is 3. Okay, so now we just want to define this sequence in a recursive form. So we're going to say we have the sequence u sub n for all values of n starting at 1 going all the way to infinity, with the first term of this sequence being -5 and all terms in the sequence being equal to the preceding term plus 3. And this is true for all values of n greater than or equal to 2. So we have an arithmetic sequence where the common difference is 3, and here it is defined in a recursive form. So in this example, we're going to be given the first two terms of an arithmetic sequence, and then we're going to find the common difference, and then write the sequence as a recursive function, give the first 7 terms of the sequence, and then graph the sequence. So to find the common difference, remember we can just take any term and subtract the term that comes before it. So in this case, 4.5 minus 3 will give us 1.5. So our common difference is 1.5. Now we're going to write the sequence as a recursive function. Well, our sequence is u sub n. So as a recursive function, we're going to say u sub n from the first term all the way to infinity, with the first term being u sub 1, which is 3, and then any term in that sequence is the preceding term plus that common difference. And this is for all values of n greater than or equal to 2. Now we're going to give the first 7 terms of the sequence. And to do that, we're just going to enter in this recursive function into our calculator. So take out your TI-84, turn it on, and make sure that you are in sequence mode. So go down, hit mode, go down to sequence, and hit enter. Then we'll go to y equals. It already is default to say that the n min is 1, so that's where we're saying our minimum term value is 1. Our function is going to be u sub n minus 1, so second 7 to get the u, parentheses, n minus 1 plus 1.5. Okay, so that's our function, and then just move down one more to say that our first term is 3. So if we hit second graph, we can look at the table, and here are the first 7 terms over here on the right. And then if we hit graph, you can see the graph of that arithmetic sequence. And if you notice, this graph looks a lot like a linear function. If we were to draw a line through these points, it would be a straight line. And the equation of a linear function can be written as y equals mx plus b. And what's interesting is, if we write the arithmetic sequence in that form, it's actually called the explicit form, and we can use that to find any term in the sequence. And that's what we're going to do next. So in this example, we're going to write the explicit form of an arithmetic sequence given the recursive form. So let's start with the recursive form, and we'll say it's u sub n is equal to u sub n minus 1 plus 4. And remember, we always have to have a starting term, so we'll say with u sub 1 equaling negative 7. So if we wanted to find the sixth term of this sequence, we'd have to list out all the preceding terms before the sixth term. So we'd have to list out the first 5, negative 7, keep adding this 4, negative 7 plus 4 gives us negative 3, add 4 again, we get 1, add 4 again, 5, 9, and then we'll get to our sixth term, which is 13. Well, the explicit form of an arithmetic sequence allows us to arrive directly at this 13 without having to find all these preceding terms. And notice, to get to that sixth term, all we had to do was repeatedly add 4. Well, we use multiplication to show repeated addition. So instead of just repeatedly add 4, all we really have to ask is how many times did we have to add 4 to get to the sixth term? Well, to get to the sixth term, we had to add 4 once, twice, 3 times, 4 times, and 5 times. So to get to the sixth term, we had to add 4 5 times. So let's look at that. To get to our sixth term, u sub 6, we started out with negative 7, and we added 4 5 times. So we had 5 4s. And you'll see we have negative 7 plus 20 does in fact give us 13. So the explicit form of a arithmetic sequence follows this form like this. It says u sub n is equal to your first term plus n minus 1 times d. So let's say we wanted to find the 10th term of this sequence. U sub 10 would be negative 7 plus 10 minus 1 times 4, or negative 7 plus 9 times 4, which gives us negative 7 plus 36, which is 29. So the 10th term of this sequence would be 29. So in this example, we're going to find the nth term of an arithmetic sequence with the first term being negative 5 and the common difference of 3. And when it says find the nth term of the arithmetic sequence, really it's just saying write the explicit form of this arithmetic sequence with these two conditions, that the first term is negative 5 and the common difference is 3. So we can write that the first term is negative 5 and d is 3. In the formula, the explicit form for an arithmetic sequence is u sub n is equal to u sub 1 plus n minus 1 times d. So in this case, u sub n, and this is what we're writing, find the nth term. Well, this is u sub n, the nth term, is the first term, negative 5, plus n minus 1 times 3. And this is fine to leave it like this, but you can tell that we could distribute and simplify this a little bit. So we could say negative 5 plus, and we'll just distribute 3n minus 3, and then just combine our like terms. And we'll write this variable term first, 3n minus 8. So the explicit form, or the nth term of this arithmetic sequence, u sub n, is 3n minus 8. So now we'll enter this into our calculator and graph this sequence. So go ahead and get out your calculator, turn it on. We're going to want to make sure we're in sequence mode. So make sure you're in sequence mode. Go to y equals, clear anything out that you have there. And we're going to enter in our n minimum is 1. Our function is 3n minus 8. So 3n minus 8, and we are starting with the first term of negative 5. Okay, hit graph, and there's your sequence. So in this example, we're going to find the 45th term of the arithmetic sequence, whose first 3 terms are 5, 9, and 13. So we know the first term, u sub 1. And now we need to find the common difference, which is u sub n minus u sub n minus 1 to give us our common difference. So we can pick either 13 minus 9 or 9 minus 5. 9 minus 5 gives us 4. So in this, we're going to be using, for this formula, we're going to use the index of 45, since we're looking for the 45th term. So that means u sub 45 is equal to the first term plus 45 minus 1 times our common difference, which is 4. So all we need to do now is just work out the calculations. 5 plus 44 times 4, and that gives us 5 plus 176, which is 181. So u sub 45 is 181. So in this example, we're going to look at how to write the explicit in recursive form of an arithmetic sequence given two terms in that sequence. So suppose we have our sequence u sub n. Okay, so u sub n is an arithmetic sequence, and two terms of that sequence are known. So u sub 6 is 57, and u sub 10 is 93. Well, we need to first find that common difference. And remember, the graph of an arithmetic sequence is a straight set of points, and the common difference acts as the slope of that line. So here we have the 2 points needed to find that common difference, 6, 57, and 10, 93. So we can just apply that slope formula, 93 minus 57 over 10 minus 6 to get 36 over 4, which is 9. So our common difference, so let's write our information over here, d is 9. Well, in order to write the recursive formula, we need the first term, and since the explicit formula can be applied regardless if the first term is known or not, we'll use the explicit form to work backwards to get u sub 1. So remember, for the explicit form, u sub n, that's equal to u sub 1 plus n minus 1 times d. Well, u sub n, we'll use 6. We'll say u sub 6. U sub 6 is equal to the first term plus 6 minus 1 times our common difference. And u sub 6 is actually just 57. The sixth term is 57. So 57 is equal to u sub 1 plus 5 times 9. Or 57 is equal to u sub 1 plus 45, and that leaves us with 12. So u sub 1 is equal to 12. And now that we know u sub 1 is 12, we can go back and write the explicit form of this function. We can say u sub n is equal to the first term plus n minus 1 times our common difference, 9, for all values of n greater than or equal to 1. In our recursive form, u sub n is equal to u sub n minus 1 plus 9, and that's with u sub 1 being equal to 12. And this is for all values of n greater than or equal to 2. A series is the value you get when you add up all the terms of a sequence. To indicate a series, we use the Greek letter sigma, which corresponds to a capital S, and it means to sum up. It is important to recognize the difference between a sequence and a series. While a sequence is a set of terms, a series is a sum of those terms. So this symbol sigma means to sum up all the terms of n from n equals 1 to n equals 4. So substitute 1 in for n, and then 2, 3, and 4, and you sum up all those values to get a series of 10. This summation notation can be read the sum from n equals 1 to 4 of n. So in this example, we're going to find a sum of a sequence, and we're simply going to substitute 1, 2, 3, 4, and 5 for n, in the expression negative 7 plus 3n and add the terms. So we're going to have negative 7 plus 3 times 1 plus negative 7 plus 3 times 2 plus negative 7 plus 3 times 3 plus negative 7 plus 3 times 4 plus negative 7 plus 3 times 5. So simply just add or simplify each one of these terms and then add them all up. So we have negative 7 plus 3 plus negative 7 plus 6 plus negative 7 plus 9 plus negative 7 plus 12 plus negative 7 plus 15. Okay, all of this becomes negative 4 plus negative 1 plus 2 plus 5 plus 8. So the total of this series is 10. So in this example, we're going to use the calculator to first write out the first 8 terms of this sequence, and then we'll add up all the terms from 1 to 50 of this sequence. So turn your calculator on, and this time we're going to go to second stat and go to our lists, and we're going to go over to ops, down to number 5, which says sequence. Now your screen may look different than this. It may just be blank, but you're going to enter it in the same way, just with a comma in between each part. So we're going to enter in the expression 7 minus 3n. I'm going to go down. You may hit comma. Our variable is going to be n. So again, hit comma or just go down. We're going to start at the first term, and we're going to end at the 8th term. Enter, enter, enter. So if you didn't see that original screen, this is probably what you should have. Hit enter and you'll see the first 8 terms of the sequence. And you can just scroll over to see all 8 terms. Well, now we're going to enter in that same sequence, but we're going to find the series from 1 to 50. So we'll go back to list, but this time we're going to go over to math, and we're going to go to sum first. So all we're going to do is we're going to put the sum in front of the same thing we just did. Enter, and now we're going to hit second list again, and we're going to go back and do the same thing we did in the first problem. The sequence of 7 minus 3n, our variable n, we're going to start at 1, except for in this time we're going to end at 50. Enter. So the sum of this sequence going from 1 to 50 is negative 3,475. The partial sum of an arithmetic sequence, indicated by S sub n, is the sum of a limited number of terms of a sequence, like the first 10 terms or the 5th through the 100th term. The sum of the first k terms of a sequence is called the kth partial sum of the sequence. So for example, for the even numbers, S sub 1 means the sum of the first term of the even numbers. That's just 2. S sub 2 is the sum of the first 2 terms, so 2 and 4 make 6. S sub 4 is the sum of the first 4 terms of the even numbers, so 2, 4, 6, and 8 make 20. Here are 2 formulas that can be used to find the kth partial sum. Notice the first formula requires that you know u sub k, while the second one doesn't. And the second formula requires that you know the common difference, while the first one doesn't. In this example, we're going to find the 12th partial sum of the arithmetic sequence negative 8, negative 3, 2, 7, and so on. And with any arithmetic sequence, you want to know the common difference, so we can take any term and subtract the one that comes before it. 7 minus 2 will give us 5. So our common difference is 5. And since we're looking for the 12th partial sum, we want to know the value of the 12th term. So we can use the explicit form of an arithmetic sequence to find the value of the 12th term. So u sub 12 is equal to the first term plus 12 minus 1 times the common difference. And we just simplify this. Negative 8 plus 11 times 5, which is negative 8 plus 55, which is 47. So we know that the 47th term is, the 12th term is 47. Now we can apply our partial sum formula. We can say the sum from the first to the 12th term of u sub n, meaning our sequence, is 12 divided by 2 times the first term plus the last term. And we're saying our last term is the 12th term. Then 47 minus 8 will give us 39. So we have 6 times 39, which gives us 234. So the 12th partial sum, that means the sum of the first 12 terms of this sequence, is 234. So in this next example, we want to find the sum of all multiples of 3 from 3 to 333. And this sounds a little tricky at first, but all we need to do is write down some of our true information, and we'll work from there. So this sequence, the multiples of 3 would be 3, 6, 9, 12, okay, and so on. Now another way to think of this sequence is 3, well, the multiples of 3, we get 3 as 3 times 1. We get 6 as 3 times 2. We get 9 as 3 times 3. Okay, 12 is 3 times 4. So 333, what number of the sequence would this be? Well, 3 is the first term, 6 is the second term, 9 is the third term. So 333 is 111 times 3. So that makes 333 the 111th term of this sequence. So what we're really doing is finding the 111th partial sum of the sequence. Now that we know that, we can use our partial sum formula. And we can say that the sum from the first term to the 111th term, so the sum of the first 111 terms of our sequence, u sub n, is 111 divided by 2 times the sum of the first term and the last term. 111 divided by 2, that gives us 55.5. 3 plus 333 is 336. The product of these two is 18,648. So the 111th partial sum of this sequence, meaning the sum of the first 111 terms, is 18,648. Alright, for our last example, we're going to look at an application of partial sums. And in this example, it says that the starting salary. Alright, for our last example, we're going to look at an application of partial sums. And in this example, the starting salary for a job is $20,000, and you get a $2,000 raise at the beginning of each subsequent year. The question is, how much will you earn during the first 10 years? So we're going to find the 10th partial sum, right? The sum of your salary after 10 years. So we know that our initial salary, our initial term in this sequence, is 20,000. So u sub 1 is 20,000. We get a $2,000 raise at the beginning of each subsequent year, so that's that constant growth, that constant difference. So our common difference is 2,000. So now we just need to find the salary after 10 years and then apply the partial sum formula. So we need to find the salary after 10 years. So we need to find u sub 10. And that's the first term plus 10 minus 1 times your common difference. So we have 20,000 plus 9 times 2,000, which is 20,000 plus 18,000, which is 38,000. So after 10 years, you're going to be making $38,000. Now to find the 10th partial sum, we're going to use our partial sum formula. So that's the sum of the first term to the 10th term of our sequence, u sub n, is 10 divided by 2 times the first term, which is 20,000, plus the last term, which is $38,000. So we have 5 times 58,000, which is $290,000. So if you add up the salaries over 10 years, you'll have made $290,000.